is Umar Farouk, and in this mini project, I'll be presenting a comparison between a support vector machine and convolutional neural network for image classification. Uh, the ask for this assignment or this mini project was to compare two different kind of algorithms and compare their architecture and how they perform against each other. So in this particular project, we have done exactly the same thing. Here are our table of contents. First, we'll introduce ourselves to the problem statement, which we kind of did. Then we're gonna look into like support vector machine and neural networks, do like an overall comparison, look at the literature review, and after that we'll have a proper comparison between these two algorithms. We'll start with the data preparation process. Since it's an unstructured data, we'll be looking at images. Um, so we're gonna compare the data preparation process for both the algorithms. Then we're gonna look at the architecture that we have used, and after that we're gonna do some performance comparison, and at the end we'll test it with a new image, both of the algorithms. And at the end we'll have our conclusion and references. So uh, according to the literature, support vector machines are, with their kernel trick, are great algorithms to do classification. It takes a lower dimensional features to a high dimensional space where it can, even if the data is not linearly separable, it can separate it linearly by taking it to a higher dimensional space. Similarly, the whole architecture of convolutional neural network is actually being designed for image classification task. It has certain filters before you actually feed the output from the filters into a deep layered neural network or a fully connected neural network. So they work in both of the algorithms work in two different ways, uh, mainly because of how the architecture is designed. All right, so let's get right into the comparison. For SVM, we know that SVM algorithm usually takes the data as an input vector. So for the data preparation of support vector machine, we have to prepare our data or our images. In this case, we're going to be using the images of cats and dogs, and we'll try to classify them. First of all, we'll try to classify the data that we have available, and then we're going to test it with a new data set. Yes, we will actually do the split between our testing and training, but even after that, we're gonna like download a new image from Google and try to run our algorithm on that image, and let's see how it works. So what we're gonna do is that first of all, we're gonna resize the image because we'll have multiple sizes of the images available in our data set. So the algorithm, the SVM, would ideally assume that all the images are at the same size. So we're gonna resize the image. In our case, it's by 64 by 64. Um, we can go as low as like 28 by 28, or we can go to higher dimensions too. But for SVM, I would recommend to use lower pixels because the computational time and cost will kind of try to lengthen the process. So in this case, we used a 64 by 64, and honestly, it took a lot of time with different kind of kernels, especially if you want to do a hyperparameter tuning for SVM. It's gonna take a lot of time. In this case, we're gonna discuss it in the upcoming work that it took us like more than 7 hours just to tune the parameters, but we ended up not doing it. Alright, so let's load the data set and start the comparison. Alright, so what I've done here is that since I'm using Google Colab, and you guys would know that you cannot actually read the files directly from your local machine into the Colab. So I have to mount my Google Drive and save the files in the Google Drive. Now that's not the only way to get the data set into Google Colab. You can also directly download it from Kaggle. I think we've done that for the convolutional. You can use the same data, but just to try a different method, we did that over there. So once we mounted our drive, we actually took the path of the directory where all the images are stored. In my case, it's over here. In your case, it might be a little bit different. And then, since we don't have any labels for it, so we created labels or categories for our data, and another list for data, which is going to store our unstructured data into a structured form. All right, so the process goes in a way that first we have to access the path of the folder. So in my case, it should be in Drive. When you go to Drive, you will have uh, that's my drive, and then you have a folder this under this name, homework for data. So in your case, it could be anything. So just make sure that change your directory path. So I'm using OS package from or OS library from Python, which is gonna give me access to the path folder, the path of the folder, and after that, I'm gonna label it based on the categories that we have. So the first folder is cats, so I have cat as the first label, and the second folder on this path is dog, so I have dog as the next label. After that, what we're gonna do is that we're gonna pre-process our images. So we're gonna access each image, and then we're gonna resize the image to 64 by 64, and then we have to flatten it. What flattening does is that it actually changes the 2D array into 1D array, which makes it a lot easier for the SVM to draw a decision boundary. And then we're gonna append the image, which is gonna be a single D array with its label, to the data list. Now, you can, if you don't want to repeat this whole process again and again, you can also save it in a .pickle file format using pickle library. In this case, I've done that, but I've commented out since I'm going to run this code live, which I already did. You can see that it's already been run. It took me around 3 minutes to run this code. All right, so that was the whole data preparation process. I have to resize, I have to flatten, I can normalize the image too, which I haven't done in this case. That would be an additional plus if you do that. Might help you out in it might help out the SVM, and well, I would definitely recommend to do it. I'll probably add it after this video. All right, and like I said, we had another method to use to actually get the data directly from Kaggle. So you have to use your Kaggle API. So first of all, you have to download a file for the API. It's going to be a JSON file, and load it over here. I don't have it over here since it's already connected to my Colab. And then you have to run these two particular codes. Once you run that, this is the address for the cats and dog, and this is for the connecting to Kaggle through a API. So once you do that, then you'll have your zip file. So you have to unzip the zip file. So you have to extract all the contents, and when you do that, you'll have this. So now the pre-processing for convolutional neural network is very easy. Well, in fact, if you have a same size of image, you don't even need to do any pre-processing. The algorithm or the convolutional neural network will do that for you. But in our case, since I'm using Google Colab and I don't have a very strong machine, so I had to do a little bit of pre-processing to actually reduce the batch size. What it does is that it only feeds 32 images at one time to our neural network, so that our RAM or random access memory is used more optimizedly. All right. So after that, and at the same time, we already have a training and testing dataset folders in the cats and dogs. So we have used their paths. So what are we doing over here is that this particular function, it actually works as a generator function, and it generates the training data set in the batch of 32, and it also resizes it, and it gets its data from this particular directory. So that's another plus with using the convolutional neural network, is that you can use the generator functions from the keras to just generate the data when it is required. What generator function does is that it actually like normal function would restart if you rerun it, restart from like the initial value. The generator function starts from the previous value where it left off. So that's what it does. So if you do run this one time, so it's gonna take the first 32 values. If you run it second time, it's not gonna take the first 32 values again. It's gonna take the next 32 values. So that's what it does. Similarly, for the validation, which is our training testing set, you can see that it's in my contents in the test set. If you open that, there's another test set folder. So you will see this test set, test set. All right. After that, it is highly preferable to normalize your data for a neural network, any kind of neural network. It would be more preferable to normalize that. So that's what you did. That's what we did, both the training and the validation. All right. Now coming to the architecture. So in this for this particular problem, we have used a polynomial kernel as an architecture. We have left gamma to be arrow, which is one over n times features, and our error control, which is c, is equal to zero point 0.1, which is uh, relatively a wider margin, I would say. And the reason why we did that is to prevent the overfitting. And the reason why we actually picked polynomial kernel over an RBF or any other kernel is that since images do have intricate details, and one thing to be noticed, one thing to be noted about the images is that the pixels are actually related to each other, and that's what you want in your architecture of the algorithm that you're using, that it can pick the information from the connection between the pixel, and that's what polynomial does. uh, After that, we actually fit our training and testing data to our model. And you can also, and these parameters, these hyperparameters have been picked using trial and error, like I said before. The reason why I did that, it took me more than 7 hours just to run this code to pick up the best parameters out of this grid using grid search CV for this particular algorithm, and it took 7 hours. It was still running, and it could not give me it didn't give me any results. So then I had to use trial and error. So I have to manually change it, run it, and see how it performs. And this was the one where I got the best performance. All right, coming to convolutional neural networks. So now the difference is really obvious. If you look at it in convolution, you will have uh, more flexibility in terms of using your filters. Well, if you look at the architecture itself, like the word filters that I've used, which is in first case we're using 32 filters, in the second we are using 64 with the kernel size of 3 cross 3, and padding valid, which means that there is no padding, and we're using value as our activation function. And if you look at the input shape, the input shape is actually a tensor rather than a vector, which we had in a case of SVM. All right. So if you look at the code starts with sequential, which means that everything that is going to come after this is going to use in sequence, and that's a function from Keras again. So in our first filter, we use convolution with 32 filters with a kernel size of 3 cross 3 with no paddings, and that's our input shape. After that, the data gets pre-processed with the batch normalize. We actually normalize the batch in between, and then we feed it to the max pooling layer with the pool size of 2 cross 2, and strides 2 means steps of 2. Again, padding is valid. Um, After that, we actually increase the filter size from 32 to 64, and then after that we actually increase the filter size to 28, and all the information that comes from these three filters is flattened and then fed into a dense layer or fully connected neural network. And here's the full architecture of our model. By just using calling model dot summary function, we can actually, or method, we can actually get the whole summary of our model. So you can see that you have more flexibility, more options available, more options specifically designed to filter out images in convolution as compared to in our support vector machine. Alright, coming to performance now. So since our models are ready, so we ran the models and we got up to like 50 almost 59% of accuracy or 60% accuracy. Sometimes I would get like 60%, sometimes I would get like 59, 58%. But it was lingering around like 60% mark, which which tells us that our SVM is just 10% better than than flipping a coin. It is not great, uh, but it still is okay. Since we've used a very in our data set we had 10,000 8,000 images for training, so which is kind of heavy for SVM. It was obviously taking more time than convolutional neural network. uh, Maybe if we can do hyperparameters tuning, or maybe we reduce the complexity of our images, it might affect the performance. It might bump it up to like 70%. But as for these images, this is the best that we were getting, and which is not great when it comes to image classification. So, so according to the predictions on our testing, our first testing label was cat, and this is the resized display of that image, and it looks like a cat to me. Um, I don't I don't know, but it looks like a cat to me. So on a testing, it was doing an okay job. Then I actually fed a new data to it. So I downloaded this image of a dog, and then I loaded into my collab, so you can see the images already been loaded by using upload function. And then I've resized and did the whole pre-processing part that I used to do that I did for my for training my model, and then I made the prediction, and it actually surprisingly did predict it as a dog. So I was not expecting it. I was probably expecting something more erroneous info, because it's 60% is not that great of an accuracy. So I did try another image. I don't have it over here in this on this particular notebook. It predicted that as a dog, and it was actually a cat. And I did that for another one, and then there was a cat. Sorry, it was a dog, and it predicted as a cat. So it was making a lot of error, but this one came out to be good, so I just left this one. Which shouldn't be the case. I should show the errors too over here. So moving on to our convolutional neural network. In our convolutional neural network, our architecture was ready. So we're gonna use Adam as an optimizer binary cross entropy, since it's a classification problem. So that's gonna be our last function, and metrics is gonna be accuracy. So we're gonna look at the accuracy. All right. So let's fit our training. Train DS actually contains our training dataset, and validation DS contains our validation dataset. We're gonna keep our epochs to 15. It's not a fixed rule. I've tried 20, 30 epochs. One thing to be noticed is that if you're using Google Colab, before running the convolutional neural network, change your runtime from a CPU to GPU, because if you're not on GPU, it's gonna take a lot of time, more than SVM. So I ran that. Since the number of epochs were 15, it took me 8 minutes, uh, which is higher than the SVM, surprisingly. But the SVM, if you actually change these parameters, it takes hours. Or if you want to tune it, because this is also getting tuned at the same time. So this is like the tuning time of our model, and it runs it 15 times in the batches. So we have 251 batches, and each batch contains 32 images. So it comes up to be like, if you multiply 251 by 32, so it's close to like 8,000, which is our training data. All right. So we see that there's a continuous improvement in our validation accuracy. We started like 50%, which is equal to flipping coin, and we ended up the maximum that we got was 77%, which is way over 58% that we got from SVM. So this is the performance of our training. We see that the validation, the training is keep on increasing if you're using training data. So it's kind of, if you want to categorize it, it's kind of overfitting to the training data, but it still is not doing bad job as compared to SVM. Because if you look at it, the training accuracy is almost 95%, and the testing accuracy or the validation data set accuracy was close to 77%. So which kind of tells us that there's almost like 20% difference between training and testing. And I was reading one of the books. I forgot the name. I cannot mention the name of the book. You can Google it. But if there's more than 15, there's more than 20% of difference between the accuracy of training and testing. So your model is clearly overfitting, which is the case over here. But if you look at the last function, on last function, our validation is doing very well. It's pretty close to our training. So then I tested with a new image. I downloaded this cat image from Google, and if you can see that, I just have to resize it and make it a tensor shape. I don't need to do any kind of normalization. I don't need to do any kind of flattening. Nothing is required. I just have to reshape it so that like it is the same shape as what we had in our training data set during training the model. And it predicted out as 0. So 0 is the first label. I did not actually use the labels for this model. If you look at it, the pre-processing does not contain anything that actually labels our output. While in SVM, while I was doing the pre-processing, I actually labeled it. So you can see that the categories are being used as its label. So I didn't do that. I can do it, but I was getting a little bit lazy, so I didn't do that. But 0 means cat, and to be honest, CNN was actually performing better. I've tried different new images that I've downloaded, and it was doing a much better. Only on a couple of occasions, it was misclassifying it, even though the accuracy is not that great. Again, it's close to like 77, or let's if you round it off, like let's say 80%. It's still not is not that great, but on most of the images, it was doing a better job. If we can like work a little bit more on our let's say activation functions and our filtering, maybe uh, using softmax instead of sigmoid over here might improve our performance, but I'll leave it as it is because I was just trying to check out how they compare against each other. So this is the whole comparison, and we have the conclusion at the end. So if you want to read that, you can pause the video for a moment. And these are some great references or research papers that I've seen along the way while I was doing this, especially to understand. Like you can find the code and everything within like 2 minutes over the internet, or you can even ask ChatGPT, honestly. But to understand the whole process, you have to have some kind of literature review done before you actually get into comparison. So some of the papers are a comparison, some of the papers are just solely working on one algorithm. So for instance, this one uses SVM and CNN as an image. It's a really nice research paper. I've read it. Some of them are just using CNN, with augmentation. Yeah, data augmentation was another thing that we can apply on both of the algorithms to improve the performance, which I haven't tried in this case, uh, since I had to keep up with the time constraints, so I could not do that. But like data augmentation could be another thing that can improve the performance of both the algorithms. So I think that will be it from my side. If you guys have any question, and if you're watching this on YouTube, you can leave questions down below, and I'll try my best to answer all of these questions. Thank you so much.